It's like the lowest level. It's like the ground floor in a multi-story building, right? That's why it's called the ground. It's at the bottom. So it's the lowest energy level, right? E naught's the lowest energy. So all the other energy levels, En, are greater or equal to E naught, right? But by definition. So all these ENs here are greater or equal to E naught. So now, since this is equal to the expectation value of the Hamiltonian, this, okay, can you see that since these, for these ENs, En is greater than E naught. So can you see that the Hamiltonian expectation value of the Hamiltonian will be greater or equal to the sum of this, but with a naught here, E naught? Okay? Can you see that? Okay, now I can get where I was going, but I jumped ahead too much. Now there's a constant, so you can bring this out the front here, which is done here, and then you're just left with sigma an squared. But we assumed that the trial function, the ansatz, was normalized. Right? We assumed this is normalized, which implied that the sum of these squared is 1. Right? So this sigma an squared is just 1. So this term here is just 1. And that just leaves you with E naught. Okay? So in other words, it implies that, so it is implied that, or you can conclude that, or just sort of therefore, effectively. Okay? So therefore the expectation value of the Hamiltonian using your trial function, your ansatz, is greater or equal to E naught. And that's what we wanted to prove. So we proved it. Okay? So end of proof sign, or QED. So vertical hollow rectangle here. Okay? So we proved it. Okay. Now so we know that's true. So what can you do with it? Well, we now know that the expectation value of the Hamiltonian with your ansatz is greater or equal to E0. Greater, it's not less than. Okay? We know it's greater than that. So, and here's the trick. Here's the smart, creative idea. For your ansatz, your trial wave function, choose something that you think is reasonable, given your background knowledge in physics or whatever, quantum mechanics. Choose something that you think is reasonable, and put a parameter in it, and then we can and then given your trial function, we can calculate this. We know whatever it is, it's going to be this expectation value. It's going to be larger or equal to the minimum. Sorry, the ground state energy, E naught. We know that. We've proved that has to be true, no matter what this is. Okay, we've proved that. So choose an ansatz that has a parameter in it, and then you can optimize that parameter so that this expectation value here is minimized, right? And we know it can't be less than E naught. Okay, so by minimizing it, we get closer and closer. We get as close to this as the ansatz will allow us. Now, by choosing different ansatzes, so we can actually do it in the next session. We'll do 2. We'll use 2, and we'll get different answers. We'll get different values for this expectation value, which is like an estimate, an estimation, an approximation to your ground state energy. So we'll get 2 different answers depending on your trial, which sort of intuitively makes sense. Okay, so that's the idea. So choose an ansatz, a trial function that you think is plausible given the context, the nature of the problem, and put some parameters, or at least one. Put a parameter into it, and then you can. This expectation value will then depend the value of it will depend on that parameter, and then you can use high school calculus to minimize this expectation value, and that will get you closer to this, right? So I mean, whatever your trial function is, it's going to be greater or equal to E0, right? We proved that. That's a mathematical proof. Okay, so this parameter is adjustable. I mean, you can tune it in the sense of you can differentiate it such that this value here, this expectation value, takes a minimum value, minimum, like maximum minima theory that you did in high school calculus, right? When the gradient is 0, that kind of high school stuff, easy. All right. Okay, so now let's actually try something. So the context is, we're talking about the SHO, right? The simple harmonic oscillator. We're going to guess, for the ansatz, the trial function, that it'll be something of this form. Let's say, so exponential minus alpha x squared. And you may query, well, where did this come from? Just fell out of the sky, right? I guess that's a little bit of an ICBST, okay? But it's sort of plausible because it's sort of Gaussian. If you know some statistics, the bell curve, the normal distribution curve, takes something of this form. You may have prior knowledge a bit of the simple harmonic oscillator solutions, so this is sort of somewhat similar. Anyway, discussing where the trial solution comes from is a bit of a black magic, a bit of an art. So anyway, we'll try something. So let's just try this, okay? Now actually, this example actually gives the exact answer. Surprise, surprise. Getting dark again? It's 5. And I better switch on the light and put on my cap. Just a minute. The cap, still bright light. Still haven't got round to changing lighting on the ceiling. Okay, so we'll plug this in. We will evaluate for this value of u of t, this ansatz here. We will first normalize it. Remember the ansatz we normalized before, so that will give us some normalizing factor that will depend on the alpha. Okay, and then with that normalized wave function, the ansatz, normalized ansatz, we'll plug that into here and here. We'll evaluate now the Hamiltonian. Now that Hamiltonian will depend on what type of system you're talking about. Well, we're talking about the simple harmonic oscillator, SHO, so we know the Hamiltonian for the SHO, so we can plug in those terms. We can calculate this expectation value. The result will depend on alpha, and then we differentiate this result, this expectation value, with respect to alpha to get the minimum expectation value. And surprise, surprise, the exact answer. It'll come out. For to be a half h bar omega, which you know from simple harmonic oscillator SHO theory. That's the ground state energy, the lowest allowed simple harmonic oscillator SHO eigenvalue for the energy, the eigenenergy, right? Half h bar omega. Right? Well, I'll just continue straight on the next session.